Hey everyone, and welcome to today's Explainer. Today, we're diving into something that literally feels straight out of a sci-fi blockbuster, but trust me, it is incredibly real and absolutely crucial for our future. We're going to be unpacking some thrilling new research led by Oxford University and a tech startup called the Outer Solar System Company. Basically, they're paving the way for entirely new strategies to protect Earth from hazardous asteroids. So let's jump right in and see how science is literally working to save the world. So here's the million-dollar question. Can nuclear weapons actually deflect an asteroid? I mean, it's the ultimate Hollywood premise, right? We've all seen those movies. A giant rogue space rock is hurtling toward Earth, and humanity's absolute last hope is to just nuke the thing. But if we strip away the dramatic soundtracks and the CGI explosions, could we actually pull this off in real life before a global catastrophe hits? Well, this isn't just movie magic anymore, folks. This high-stakes scenario is exactly what's driving planetary defense research right this very second. Section 1. The nuclear option, Hollywood premise versus reality. Right now, our planetary defense playbook basically gives us two wildly different options. On one hand, we've got NASA's incredible 2022 DART mission. This was a massive game changer because it proved that the kinetic impact method actually works. Literally just ramming a spacecraft into an asteroid to knock it off course. It's proven, sure, but it comes with some pretty huge risks. For one, a kinetic impact might just slow the asteroid down instead of actually bumping it into a safe orbit. Or worse, it could shatter the asteroid into a bunch of uncontrollable fragments that still end up hitting Earth. Yikes. Then, on the other hand, there's the nuclear option. Now, this packs way more of a punch, but it is completely untested. We can't just guess which one to use. The real-world physics of blowing up or deflecting space rocks is unbelievably complex. Which brings us to Section 2, the knowledge gap. The great modeling mystery. Okay, so to actually choose safely between a kinetic strike and a nuclear detonation, scientists desperately need to know exactly how asteroid materials react under extreme stress in real time. If we don't know that, we risk causing that chaotic fragmentation we just talked about. And here is where we hit a terrifying roadblock. It comes down to a staggering number. 7 times. The data we have on how these materials respond to intense stress is just incredibly limited. Depending on whether researchers look at the asteroid material at a micro level or a macro level, their estimates on when the rock will actually break apart can vary by up to 7 times. Think about that. When you're dealing with the survival of the human race, a 7-fold margin of error in your defense model is pretty much a nightmare. We absolutely need better data. Enter Section 3, the CERN experiment, shooting asteroids with protons. So how do you solve a mystery this big? You design a completely groundbreaking experiment. And honestly, where better to push the absolute limits of physics than CERN? For this test, researchers didn't just grab a random rock from the backyard. No, they used an actual sample from the Campo del Cielo iron meteorite. They took this literal piece of space iron to CERN's high radiation to materials facility, and they blasted it with a high-energy proton beam using the superproton synchrotron. The really clever part here was firing the beam in extremely short, intense bursts. This meant they didn't completely obliterate the sample and could actually measure its reaction in real time. To do that, they used advanced thermal sensors and laser Doppler vibrometry to track the surface vibrations. It was an incredibly precise setup, specifically designed to mimic the insane energy of a real deflection attempt. And that leads us to Section 4, an unexpected discovery, the plot twist. Now, whenever you blast a meteorite with high-energy protons, you know you're going to get some cool data. But what these researchers found completely turned their expectations upside down. The lead researcher dropped a massive surprise, noting that analyzing the structural changes under radiation at a micro level showed the material's strength could significantly increase, perfectly aligning with prior test data. Let that sink in for a second. They were literally looking for the exact breaking point, the moment the asteroid would deform or shatter under a nuclear-level impact. But they found the exact opposite happening on a microscopic level. Instead of blowing apart, the material's strength actually amplified by up to 2.5 times. During the experiment, the meteorite sample did initially soften and deform, which, makes sense when you hit something with a giant beam of energy. But then, plot twist, rather than vaporizing, its internal structure actually shifted, and this piece of space iron became 2.5 times stronger. Just wild. Okay, so why on earth does this happen? Well, the scientific term for this is strain rate-dependent attenuation. Basically, it's a phenomenon where the harder an impact is, the more efficiently the material dissipates and absorbs that energy. Think about it like this. The harder you hit the asteroid, the tougher it gets. This is a massive breakthrough. Scientists now believe this internal stress distribution perfectly explains why we've always seen such huge discrepancies between quiet laboratory tests and the actual real-world evidence of how meteors behave when they crash through Earth's atmosphere. If you take away just one single thing from this whole explainer, please let it be this. Asteroid mechanical properties are dynamic and they change in real time under stress. They aren't just these static, boring, unchanging rocks floating out in a vacuum. When they're subjected to the intense forces of a deflection attempt, like a spacecraft ramming into them or a nuclear blast, their very structure reacts and transforms. This completely rewrites the rulebook on how we have to model future planetary defense missions, mostly because all our old models just assumed these physical properties stayed exactly the same. Moving on to Section 5, Future of Planetary Defense, Preparing for the Unknown. All right, so now that we know asteroids actually dynamically harden when you strike them, what does this mean for, saving Earth from total destruction? Well, we've solved one massive modeling mystery, but space is huge and our work is really just getting started. The researchers already have their next steps lined up. First, we've got to move beyond just iron meteorites. That Campo del Cielo sample give us phenomenal data, but iron is just one type of space rock. Second, we urgently need to test diverse asteroid compositions. I'm talking rocky, icy, carbon-rich, you name it. Every single type of asteroid might react totally differently to a nuclear or kinetic strike. And finally, the big goal is to gather all this comprehensive data and feed it into robust, highly accurate global defense models. And that leaves us with one critical, honestly kind of chilling question to think about. If the next asteroid hurtling toward Earth isn't made of iron, will we be ready? This research from Oxford and CERN proved that our basic assumptions can be wildly wrong, and that at the micro level, the physics of space rocks are full of total surprises. We've taken a giant leap forward in figuring out how to safely use the nuclear option, but the clock is ticking. The race is officially on to test every other material in the cosmos before a real threat shows up on our radar. Thank you so much for hanging out with me for this deep dive into planetary defense. Keep asking questions, keep looking up, and I will see you in the next explainer.